Morning, this is wave behaviour of particles. We've been looking at light behaving as a wave and a particle. Now we're going to look at the fact that particles might behave as waves also. Particularly, we'll look at the electron and the fact that we've been looking at this particle as having a kinetic energy in most cases, half equal to half mv squared. Of course, this is the mass, this is its velocity. We also need to look at the particle as having wave-like properties. If we look at its wave-like properties, then we would be interested in its wavelength. Wavelength is equal to Planck's constant over its momentum. So it's still related to its mass and velocity, or this can be equal to Planck's constant over just saying momentum there. We found that electrons have wavelengths of 10 to the power of minus 10 to 10 to the power of minus 11 meters, thereabouts, depending on their energy, of course. Of course, this is the energy here related to half mv squared. I'll just write this in here, this information. This is momentum for clarity. And this is Planck's constant. So essentially what we're saying is that matter has a wavelength. I should do that in green. Matter, or particles, they're saying, wave behavior of particles. Wave behavior of matter probably sounds better. Matter has a wavelength. Let's go to a problem. Here. Incidentally, this equation was first described by Louis de Broglie, 1925 or thereabouts. We call this the de Broglie wavelength. De Broglie wavelength. So the wavelength of matter. Calculate the de Broglie wavelength of a neutron moving with a speed of 10 to the 5 meters per second. So we have V is equal to 1 by 10 to the power of 5 meters per second. Its mass of a neutron is 1.675 by 10 to the minus 27 kilograms. From these two values we can get the momentum. Momentum is equal to mass times velocity, which is equal to 1.675 by 10 to the power of minus 27 kilograms times 1 by 10 to the power of 5 meters per second, which equals 3.96 by 10 to the power of minus 12. Oh, hang on, that's the wavelength. I've jumped ahead, sorry. 1.675 by 10 to the power of minus 22 sec newtons. Of course, you multiply the exponents here and we get this value here. You add the exponents. Okay, wavelength, lambda, is equal to Planck's constant over the momentum, which is equal to 6.63 by 10 to the minus 34 joule seconds, all over Our wavelength 1.675 by 10 to the power of minus 22 sec newtons. Lambda equals 3.96 by 10 to the power of minus 12 meters. So this is a neutron, and I always draw neutrons in a sort of a grey colour, moving at 10 to the power of 5 meters per second, quite fast, and it has a wavelength associated with it. Now look at it in two lights. Neutron. Part B says calculate the de Broglie wavelength of a sprinter of mass 90 kilos running at 10 meters per second. So we're looking in the macro scale now. And I'll just draw a picture so we get a good idea. This is a man running. Sprinter, could be a female. 90 kilograms at 10 meters per second. Momentum first, or we could just go straight to the wavelength is equal to Planck's constant over mass times velocity. 6.63 by 10 to the minus 34 all over 90 kilograms times 10 meters per second. 7.37 by 10 to the power of minus 37 meters. And what this is saying is that the de Broglie wavelength, the wavelength of something in the macro scale that weighs 90 kilograms and traveling at 10 meters per second. So a much smaller speed, of course, but a much larger mass. Macroscopic. Objects have a small wavelength. This is a very small number. We looked at kinetic energy before. Kinetic energy is equal to half mv squared. Here's an equation to show that you can get from the momentum, which is here, from the momentum of an object, you can get, oh sorry, I beg your pardon, from the energy of an object, you can get the momentum. Momentum's tied up in here with the mass and the velocity. So let's move it. I'll just call kinetic energy E. E. Bring the 2 up on the other side. 2E equals mv squared. Multiply both sides by m. 2me equals m squared v squared. The square root of 2me equals momentum, mv. From this, if you have the value for energy, of an object, of matter, you can find its wavelength. Davison-Germer, or Germer, I think it's pronounced. Um, Clinton Davison and Lester Germer in about 1927. So 1927 did this experiment, and the reason why I'll talk about in a second. They had these are atoms, very evenly spaced, by very evenly spaced atoms, uh, or in order to get very evenly spaced atoms, I could have a crystal surface. So these are the surface atoms, and I might fire electrons at it. Well, this is what Davison and Germer did. They fired electrons at it, and I'm drawing one electron, but of course they fired lots and lots of them using an electron gun. The electron was behaving as a wave, of course. They wanted to see what would happen if they had, or they wanted to see the results by putting screens around this this setup here, this experimental setup. So this is a crystal surface. It was actually nickel, and using nickel, they knew these distances here. They knew very specifically what these were. I think they're about 2.15 by 10 to the minus 10 meters. I'll check that in a second. So they fired these electrons at this surface. They set up screens around this setup, and they had a look to see what was going on. Of course, when the electrons come off of this crystal surface, where they tend to collect, where these electrons were tending to collect, you would see on the screens, you would see the screen lit up at that point. These were phosphorus screens, I think, so electrons striking them, just like the old CRT TVs, electrons striking them would cause them to light up, and you could see very closely, or you could see very visually why these screens, where these screens were lighting up, rather. Okay. What did they find? They found areas around the lattice. We call this crystal surface or a lattice structure, if we're talking at the atomic level. They found areas around the lattice on the screens, the reflection of the electrons, where constructive interference appeared occurred. Constructive interference occurred. Occurred. Is that right? Double R? Doesn't look right to me. Occurred. No, that's not right, definitely. Okay, so these screens were showing very visually that the electrons would cause the phosphorus to light up. So we'd have these bright bands. Bright bands tended to show at a very specific angle, and that was 50 degrees to the normal. Okay, we'll just get a new screen here. This crystal surface was tending to act as a diffraction grating. We call this the Davison-Germer experiment. Uh, one thing that's different, I'll just get a picture out of our text. This is what they found. Why was this interesting? This is what they found was this. Here's our crystal lattice here, this nickel crystal lattice. The incident electron matter wave. Now, students were a little bit concerned, or a little bit confused rather, about what's going on here. The incident electrons are at some angle here. What's happening is we've been looking at diffraction gratings that appear to where light actually passes through the diffraction grating. We see similar effects when matter reflects off of a diffraction grating, so to speak. Okay, so this crystal lattice, what would tend to happen is the electrons would often just pass straight through or pass into the crystal lattice in some cases. But they would also reflect off. And when they reflected off, because we could see constructive interference, it was a demonstration that these matter waves were, or these pieces of matter were acting as waves, just like light did. Okay, so they fired 54 EV electrons. When I talk in energy of an electron, I mean its velocity, so to speak, because E equals half mv squared. So mass is fixed, energy relates to velocity, and so 54 EV electrons. If you have a stationary electron and you accelerate them through an electric field of or a potential difference of 54 volts, will essentially have mostly 54 electron volt electrons or thereabouts. What they noticed was at 50 degrees, and that's probably not a good place to write it, at 50 degrees to the normal. If I draw in a normal to this crystal surface, and or about 50 degrees, that's about 45 there, about 50 degrees. 50 degrees there. We had some constructive interference occurring. Now, so a bright band at this point. There would be a bright band on the other side as well. Bright band, where the electrons were striking the phosphorus surface. Davison and Germer were pretty smart fellas, and so they decided that this might be good evidence to show that matter behaved as waves in some cases. So we'll say that. Evidence that matter, particles, matter was behaving as a wave. So far in this course, we've looked at photons. Photons are the result of evidence that light behaves as a particle, but of course we also know that light behaves as a wave. Matter behaves as a particle and also behaves as a wave. It was just the same. So how do they show this? Well, if they could show that d sine theta equals m lambda holds for this matter wave when we have a diffraction grating, which is essentially just a crystal lattice, then we've got good evidence that, experimental evidence that matter does behave as a wave, in fact. So they knew this. 10 to the power of minus 10 meters was D, approximately this distance between the nickel atoms. Sine of 50 degrees would equal to, of course, this was the first maximum. This is the first bright band, so m equals 1 lambda, the wavelength of the wave. So theoretically, here's how we calculate it. We know the energy equals 54 eV. Change that to joules, of course. 54 multiplied by the electron charge. .64 by 10 to the minus 19 joules. Of course, that is equal to half mv squared also. From this, I'll move down. Sorry, I was going to move across. From this, we can go and find V. V is equal to the square root. Let's have a look. V 8.64 times 2 times 8.64 by 10 to the minus 19 joules over m. And m for an electron is 9.11 by 10 to the minus 31 kilograms. We get a velocity of 4.355 by 10 to the power of 6 meters per second. Now we'll come up here. Momentum equals mass times velocity, which is equal to 9.11 by 10 to the minus 31 multiplied by the velocity, 4.355 by 10 to the 6 meters per second. 3.968 by 10 to the power of minus 24 sec-newtons. De Broglie wavelength. 6.63 by 10 to the minus 34. All over our momentum, 3.968 by 10 to the minus 24. 1.67 by 10 to the power of minus 10 meters. That's the de Broglie wavelength, calculated knowing the initial energy of the electrons. Okay, that's what the de Broglie wavelength should be. Experimentally, and this took a lot longer for them to calculate, of course, they noticed reinforcement when I say reinforcement, I mean this bright band here. We noticed a reinforcement line or a constructive interference occurring at 50 degrees. It doesn't look like a degrees insignia. Degrees. And they knew the separation of the nickel atoms in this very nice uniform crystal lattice. If they could show this, d sine theta equals m lambda, if they could show lambda using this experimental technique, then it's good evidence for matter behaving as a wave, or very, very strong evidence. Conclusive evidence, perhaps. Lambda is equal to m equals 1, so this is the first reinforcement line here, this first bright band. At 50 degrees, d is 2.15 by 10 to the minus 10 meters. Yes. Nickel atoms, the separation of the nickel atoms, or our diffraction grating, times sine of 50 degrees is equal to 1.65 by 10 to the power of minus 10 meters. Have a look at this number here, and look at this number here. Yes, it's all right. Just 1 second. So these two numbers here, this number here and this number here, this is the theoretical evidence for the wavelength of an electron, and this is the experimental evidence. They correlate. The two numbers, experimental and theoretical, correlate. Very close correlation. And from this, they get matter behaves as a wave. And that's the Davison-Germer experiment, 1927. That's all.